Okay, so let's go on to 1310. So suppose you want to find the extrema of fxy with the constraint. Let's suppose in this case it's x squared plus y squared equals k. In general, you put some function of g of x here. So you first parameterize your g of x equals k. Say we parameterize it as rt equal xti plus ytj. So in our case, let's draw a picture. So we have then in our case, the constraint is a circle. So you'd have a circle in the xy plane. And then you have your surface above that, so it might be there, up to that, maybe down to here, down, 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 back up on this side, down, 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 a bit higher, things like that, say. So, like this. So it looks like a roller coaster. So you can think of it like a roller coaster here. So here's my f up here. And down here is my RT. In this case, it's a circle. And down here, it's also the xy plane. So you can imagine walking around this circle, and above you, you'll see the surface. So you're walking around a circle, looking at the surface above. And as you walk around, looks like right here, for example, when you get to this point, you see the highest point on the surface there, and then it goes down, and back around, and up, and down again. So we're trying to find the high points and the low points. So need to find extrema so it's pretty much the surface, so F's going to be a surface if you graphed it, but we're restricted to being on the walking around a circle only. So pretty much you could say that is F of RT. That's saying in the xy plane you're constrained to being on the circle, or whatever constraint you have. In this case, it's a circle. So by the chain rule, we have then the derivative of f of RT. So using theorem 10, it's partial derivative of f with respect to x times dx dt plus partial derivative with respect to y times dy dt. Okay, so let's keep going. Okay, so keep going up here. So we wrote it up here. So then we can write this as f with respect to x evaluated at r of t plus or times, I say, x prime of t plus derivative respect to y r of t times y prime of t. We can then write this as the gradient. So actually maybe write this first. Write like this. RTI plus FY RTJ dotted with x prime of TI plus y prime of TJ. And this guy is the gradient. This is the gradient of f composite RT dotted with x prime TI plus y prime TJ. So now, say f, so f of r of t0 is an extrema. This implies then, from math 150, because it's a function of just t here, means the f prime of r of t0 is 0. So hence, plugging in up here, we'll have then that the gradient composed with r t0 dotted with x prime of t0i plus y prime t0j is 0. Okay. This implies then since the dot product of these two is 0, it implies that the gradient is perpendicular to, so it implies our gradient guy is perpendicular to, that's my symbol for perpendicular to our derivative. Y prime t0 j. I guess you could just write this as r prime of t0 if you wanted to. Okay. Okay, so next, say g of r of t equals k. So on this side we have a function of t and equals a constant. So this implies then the derivative with respect to t. So it implies derivative would equal 0. Just taking derivative on both sides with respect to t implies this. And then we can also, by chain rule, I'll have that, so 0 equals g prime of r t. So it equal then g derivative with respect to x evaluated at rt dotted with x prime of t plus gy evaluated at rt times y prime of t. We can write this then as gx rt at I plus gy rt j dotted with x prime t I plus y prime j. So this has to equal 0, so you can set equals here, 0, 0 here. This implies, well, this is also the gradient here, so the gradient of g at rt, this guy, implies then that the gradient of g is perpendicular to the r prime guy here. So again, you can call that r prime of t if you want to. Okay. Okay, so summarizing what so now we have, we've shown the gradient of f at r t0 site is perpendicular to r prime of t0, and the gradient of G also perpendicular to the same R prime. So these are all in the xy plane. So if this guy is perpendicular to this one, this guy is perpendicular to the same one, implies these two would have to be parallel. This implies that the gradient of F is parallel to gradient of G. And again, in a sense, both are in xy plane. So I'm defining here this guy here to mean parallel. So this implies then, hence, we can say that the gradient f at, so maybe make a definition here, say let R of t0 equal x0, y0, then we have gradient of f at x0, y0 equals lambda times gradient of g at x0, y0. First some lambda. Some real number. So we call lambda the Lagrange multiplier. Okay, so now let me just state the Lagrange multiplier method. So let's do that now. Okay, so let's state the method of Lagrange multipliers. So 1, solve system. System here is fx xy equal lambda gx xy, fy equal lambda gy, and g of x equals c. So then 2, evaluate f at each solution from step 1 to determine max and mins. Okay, so that's the method of Lagrange multipliers. We'll look at an example now. We'll look at an example in the next video.